Hello and welcome to exploring the benefits of waterjet cutting, specifically between waterjet and plasma. My name's Benji Mera. I'm the product manager here at WARDJet, and I'm joined as always by Jeff Day, senior applications engineer for WARDJet. We wanted to talk to you about an issue concerning that we get presented quite a lot at WARDJet. Is someone looking for the next piece of equipment in the shop? Should it be waterjet or plasma? And they're trying to decide between the two. So we wanted to show you a couple of the differences about it, about the two technologies today, and then show some of the versatility of waterjet. Jeff's going to run us through quite a bit here at the tail end of the webinar. So first of all, plasma as a cutting process. Clearly, it's a accelerated jet of ionized gas where the plasma is actually doing all of the cutting by melting the material, and then that melted material then gets forced out of whatever plate you're cutting, and that's what's going to be causing your separation. Thin material, usually what you're cutting up to about an inch, inch and a half. I do know some machines go thicker, but that really depends on the gas mix and amperage of the machine as well. Some of the benefits of plasma, there's no denying it. It is very, very fast. If you're cutting sheet steel and that's really all you're cutting, you're not going to find a better process for you. If you're doing, near net shapes or things like that, and you do have a secondary process that you need to put on the back end of that. And it's also very inexpensive. The actual operating of it isn't too expensive, and also the initial cost of entry is relatively low as well. But there are some downsides to plasma. Biggest one for us that we see is the heat affected zone. Clearly you're heating up the material, you're melting it, and sometimes that heat can actually change the material properties. And this is a particular concern when you're talking about certain alloys, especially in, say, an aerospace application. You will also have some secondary processes needed. That melted material on the back side of the material, as it gets forced out, sometimes does harden, and that's what they call dross. So you may have to clean that up in order to get a smooth edge there. Another safety issue you might have is the arc safety. Clearly, it's very unsafe to look directly at the arc as it is cutting. Can cause eye damage and even blindness. So that is another thing to consider as well, depending on your shop. But the biggest limitation we find with plasma is that the material that you can cut, which is it has to be conductive in order for the plasma operation to work. So you're mostly looking at mild steel, stainless, aluminum, but you can also do some different materials like copper, brass, and some different alloys depending on the gas mixture that you're using. So when we look at waterjet, different process, even though it may seem somewhat similar when you look at it from the outside. So waterjet is an accelerated stream of water, super high pressure, and then we introduce abrasive media, usually crushed garnet, to actually do the cutting work. Now, what we're actually doing is controlled accelerated erosion. So the same process that created the Grand Canyon, any valley, stream, things like that, over millions of years, we're just doing that very, very quickly, and we're telling it exactly where to go. The material range for waterjet is much wider, goes from very, very thin, maybe stacked materials that we can do, up to 12 or more inches thick. You're really only limited with waterjet by what you can fit under the waterjet head and how much time you have. So a couple different things you can do with waterjet. You can cut with pure water. That's no abrasive in the stream. It's just the power of the water is doing the cutting. Typically anything that you can cut with a blade, you can cut with pure water. So foams, rubbers, papers, some plastics and things like that, and some different elastomers as well. And then there's also the abrasive cutting, which most people are aware, and where we really do stack up right against plasma. And that's where we introduce the abrasive in there, and we can cut anything from steels to glass to Kevlar, bulletproof, glass, things like that. Whatever you can put under the waterjet, we can cut it. So some of the benefits of waterjet is going to be the cold process. Since it is erosion, it does not actually change the material properties. So the properties are the same edge to edge of that. And as we mentioned in some of those aerospace applications and alloys, extremely important that there's no weak spots in any piece of the material. There's also no gas mix or tool changes between those materials. So you can see some of the processes we're doing right now could be done all on the same setup. Multi-headed cutting on foams, 5-axis beveling on stainless. Doesn't really matter. The same basic process is running on those. The only difference that we're seeing is the speed at which we're cutting those materials. And then the most important thing about waterjet and where this really stacks up against any other technology is the versatility of their waterjet has the ability to process the widest range of materials. So from a plastic to a wood to glass to 12-inch wasp alloy. Doesn't matter. As long as you can get it under the WaterJet head, it can process it. And that's really where the decision comes in between WaterJet and plasma. If you're only cutting one material and that happens to be conductive, say 1.5 stainless steel, then plasma might be the right match for you, or the right pick for you. But if you're not sure what's going to be coming up next and you may have some other materials that you need to process, that's when really WaterJet starts to shine. So there are some instances where we tell people, start with a WaterJet so you can process anything you want. If you do find that you're running primarily steel for a large part of your applications, you can get a more inexpensive plasma down the line, dedicate that to your metalworking, and then keep the WaterJet open for both metalworking and any other material that it comes to. So take some time, speak with one of our sales representatives to see what kind of system would be right for you. WARDJet, we have the largest variety of any manufacturer out there of purpose-built WaterJets if you have something specific that you want to process, but they still have the ability to process pretty much anything else that you could throw at it. So Jeff's going to now take us through some of those different materials that we can process with a WaterJet and some tips and tricks to go with those. Over the time, take some time. If you have questions, feel free to put them in the chat box below, and we'll be happy to answer your questions after the presentation. So take it away, Jeff.
Thanks, Benji. These are a few materials that we'll watch cut here a little bit. So we'll do some carbon fiber, glass, Delrin, and UHMW. Before we get to that, I was just going to show some other materials that we've cut over the years, give an idea of the flexibility of WaterJet cutting. So of course, one of the key things, WaterJet versus other thermal processes like laser and plasma, is very little heat input into the part. So a part like this out of stainless steel, I believe this was 1/2 inch thick with these narrow webs, you're able to do all this cutting without any warping due to heat. So that, of course, big thing with the WaterJet cutting. Then you, of course, look at thicker materials. Example of some 10-inch thick wasp alloy that we did. So that's certainly something that laser would never be able to get through. And I don't think plasma would be able to handle that thickness. And then you got things like hard plastics, UHMW, and nylon that if you tried to cut this on laser, for example, would give off some pretty nasty fumes. When you get into thinner materials, if you're just looking at doing single sheets of thin steel, especially stainless, aluminum, probably nothing's faster or cheaper than a laser. However, you can look at doing things like stacking with WaterJet cutting. If you are going to stack material, you just have to make sure that you clamp them together tightly so you get as little air as possible between each of those layers. But stacking is an option with WaterJet cutting. Composites, of course, a big area for WaterJet cutting. Here's some different ones where we got metal on the outside, foam on the inside, metal on the outside, and plywood on the inside. So down here at the bottom would be used in a big server room where they want to run the cables underneath the floor. So you got some different materials there that we're cutting through. Wood is always interesting to people that it can be cut on WaterJet. There's going to be a little bit of wetting when you first take it off the table, but it dries pretty quickly, so WaterJet does a nice job on wood. Sometimes we get into ceramics rather than using the typical abrasive, which is Garnet. You might have to look at using a aluminum oxide, which is a much more aggressive material and allows you to cut faster on hard materials like ceramics. And then on the water only side of things, various open cell, closed cell foams that you can cut on WaterJet. This one here, top left, cross-linked polyethylene foam, which is quite popular in the returnable dunnage area. So companies are making parts for the various car companies. They don't want those parts damaged in shipping, so they'll put them into their containers, and inside those containers there'll be cutouts with the cross-linked polyethylene of the different shapes to protect the parts during the shipping. And then over here on the right, case inserts, big area for WaterJet cutting, be able to cut out the different shapes for the tools or whatever you're putting inside your case. Cutting of various insulation foams, big market for water-only cutting. Typically materials like this, people are going to stack it multiple layers thick, basically as much as they can get under the cutting head. Usually edge quality is not so critical because this is going inside walls, things like that. So just cutting as fast as possible, and if the edge quality is a little bit rougher on the bottom, not a big deal usually. And then if you add a 5-axis head onto your machine, then it opens up all sorts of possibilities as far as cutting things at angles, and can really add a lot of value to the parts that you cut. Various durometer rubbers can be cut water only. Of course, you can also stack rubber material to increase the productivity of the system. And here's some other examples. This one down here is for bridge abutments to help reduce vibration. And then if you do have a water-only system but need to cut hard plastics, you can do that. It's going to be a little bit rougher edge than if you did this with abrasive, but that is a possibility that you can do with water-only. Then of course water-only cutting is used a lot in the food industry. Some examples of some food products that we've cut over the years. And then some other random things we've done, some balsa wood and cork and pig heart tissue. So with that, let's go ahead and look at cutting some of these materials. For any material that's laminated or composite, the biggest issue is usually delamination at the pierce point. Typically, if you try to pierce things like carbon fiber, fiberglass, or most composites, the material is going to delaminate if you try to pierce it at high pressure like you would normally pierce metals. One option to avoid delamination is to start off the edge of the material. Common application for Waterjet is to cut dog bone shapes for tensile testing. Since there are no internal holes to cut, this is an example of where you can start off the edge of the material and avoid having to pre-drill or low pressure pierce. If you have internal holes to cut, then there are two options that we'll look at: pre-drilling and low pressure piercing. So one option is to use a drill. In this video here we're cutting 1/4-inch carbon fiber. This is being cut on our Z series machine. The drill option is available on all of our abrasive machines except for the A series that we'll see here in a bit. Here we'll see the drill first go around and pre-drill all the pierce holes. Then the cutting head will go back and pierce through those holes. Effectively, we're piercing off the edge. Drilling is a very reliable way to create starter holes in composite materials. There's very little that can go wrong. You'll note that we are drilling on top of plywood. You'll want to have some sort of sacrificial material under the material you're drilling so that the drill doesn't end up going into a grate at some point. Another interesting application for pre-drilling is laminated shims. Companies will stack 50 or more layers of material, thousandths to 5/1000ths of an inch thick, squeeze them together in a fixture, and then pre-drill the pierce holes and cut. The finished product looks like a solid piece of material, but then you peel off the shims to the thickness that you need. Now let's take a look at doing some low pressure piercing on glass. We could probably do a full hour-long webinar about glass cutting. Before we watch the full glass cutting process, I wanted to preview a couple details. Here are pictures of 80, 120, and 220 mesh Garnet abrasive. As with sandpaper, the higher the number, the finer the abrasive. For metal cutting, 80 mesh is the general all-purpose abrasive. For glass, 120 mesh and finer will give nicer results. Here we see the back side of pieces of glass cut with 80, 120, and 220 mesh. You'll notice less chipping on the back side as the mesh gets finer. Here we see the cut surface. Again, as the abrasive gets finer, the edge will be smoother. There will be a slight decrease in cutting speeds as the abrasive gets finer. The other option to avoid delamination or cracking is to use low pressure piercing. If you don't have a drill available, or the material can't easily be drilled like glass, then low pressure piercing is a good option. In this technique, we put the pump into low pressure at the start of the program and make a circular motion while low pressure piercing. After all the low pressure pierces are done, the pump goes to high pressure and we go back and pierce through those holes. Similar to pre-drilling, we are now starting off of the edge of the material, even for inside cuts. Cutting glass is one of those things where programming and setup procedures must be followed very closely to ensure success. The first time you cut glass, it will probably be very, shall we say, exciting. For companies that cut glass every day, it becomes second nature. As we're watching this video, I'll point out some of the things to pay attention to when cutting glass. For the low pressure piercing, reduce your abrasive flow rate to about half of what you're using for high pressure cutting. Lower pressure creates less of a Venturi effect inside the cutting head and cannot suck as much abrasive into the head. We have both a manual style mini hopper that you see in this video and an automated mini hopper that will change the abrasive flow rate depending upon if the pump is in low or high pressure. It's important that the material is fully supported. Here, we're only cutting a small piece. If you were cutting a larger sheet, you'd want to make sure that's fully supported so that there's no undue stress in the material which could cause it to crack. You'll note the red material under the glass. It's a good idea to have a thin sacrificial layer under your glass to prevent kickback when the stream crosses over a slat. Without the underlay material, you'll see a blemish each time the jet crosses a slat. Be careful about how tightly you clamp down your material. Similar to having an uneven surface, if you clamp too tightly, the material will crack. Use a finer mesh abrasive for a smoother edge and less chipping on the backside. 80 mesh is typically used for metal cutting. 120 mesh or finer is used on glass. In this video we're using 220 mesh. For larger sheets with lots of parts being cut out of them, try to keep the material at an even temperature. You can do this by cutting underwater, or you can put a sump pump in the tank and pump water from the tank over the glass. You can reduce frosting on the top of the part by cutting underwater or applying a thin plastic top layer. Don't be too aggressive with cut speeds, or again you'll start putting too much stress into the glass and, you guessed it, it'll crack. Just take a couple minutes to step through how we would program a part for either circular low pressure piercing in glass or drilling in composites. I've got my file open here, top right hand corner, hit my next button, choose my material and thickness. Inside of the material we have a setting here for fragile, and then on the leads tab we can choose to use circular leads, and that's going to indicate to WARDCam that we either want to do a circular low pressure pierce or drill that location. Top right hand corner, hit my next button, top left hand corner can click on auto, puts the leads on there. It's got the circle there indicating either circular low pressure pierce or a drill. Hit the next button, click on CNC and save that file. And at the beginning of the file here, in this case we're doing circular low pressure piercing, and we've got the circular motions, and if we want to drill that instead, Go up Options, Edit Variables. On the Tools tab, we have this option to drill circular pierce. Turn that on, and then click on CNC File again. And now the circular pierces will be replaced with drilling. These are the codes to activate the drill. Pretty easy to do that. And now let's go on to some cutting. Here we see a couple of hard plastics being cut on our X1530 with the Apex 65 axis head. The black material is 3/4 inch or 19 millimeter acetyl or polyoxymethylene. Try saying that 5 times fast. I'll refer to it by one of its trade names, Delrin. The white material is 1 inch or 25 millimeter UHMW. These materials both cut quite nicely with Waterjet. There's no special piercing technique required. Plastics are one area where Waterjet really shines. Being non-conductive, plasma is not going to be able to cut it. If you were to try to cut this with a laser, it would give off some pretty nasty, toxic, or noxious fumes. We use a fair bit of Delrin in our equipment. Here's one example where we use it as a cover on the end of the crossbeam of the A-series. Delrin is easy to machine. We can put it on a machining center with pretty good success, and it doesn't tend to deform like some other plastics. It makes pretty good chips and doesn't screw up the insides of our machining centers either. It's pretty hard and rigid, so it's good for some structural applications. We tend to use it for low volume plastic parts that we're going to machine. If the volumes get high enough, we'll find some other material and injection mold it instead. UHMW has a very low coefficient of friction. It's self-lubricating and highly resistant to abrasion. Its coefficient of friction is slightly lower than that of nylon or Delrin, and is comparable to that of PTFE or Teflon. But UHMW has better abrasion resistance than Teflon. One place we use UHMW is under the chains on our J and L series machines. As we're cutting, please note the slight movements that the A and C axes are making. This is the taper angle control capability of the Apex 60 head. One of the benefits of taper angle control is that if you don't mind a slightly rougher edge, you can cut faster, and then the taper angle control will straighten out the side. On these parts, with the taper angle control, we measured about 1 to 2 thousandths taper on the outside, even though, as you can see, it's a little bit rougher edge, as you would expect with a Q3 edge quality.
Thanks, Jeff. So with that, we'll go ahead and start with the Q&A portion of that. So as we mentioned, please, if you have some questions on anything you saw, feel free to type that below. We'll try to get through all of them. If we don't have too many, we'll run through a few common questions and go from there. So one of the most common questions we get, and Jeff, I'll direct this one to you, is if you're approached with a new material, you haven't cut it before, things like that, what's the best way to determine what kind of cut speeds would be ideal for that?
Well, we get that quite a bit. It's one of the great things about working here at WARDJet is all the different materials that different customers will send in. Much of the time, we'll just put it up on the machine and kind of based on the hardness of the material, just kind of start at a number and go up and down from there until we get an edge quality that we like. If it's metal, we can usually work off of a feed rate calculator. We have this feed rate calculator that we can download off of our website. If you go wardjet.com and then you go to the software page down at the bottom here, feed rate calculator. You can click on this, download this to your desktop, and this can at least give you an idea of where to start for different materials, and depending on your nozzle orifice size, it'll give you a range of cutting speeds.
Excellent. So Steve asks, is it possible to abrade to a depth? Like engraving on a laser cutter. I can answer the first part there, and I'm sure Jeff's got some examples on there. It really kind of depends on what you're trying to do. If you're trying to do depth milling on there to a pre-described depth, Waterjet's not ideal. You really want to think of it as a through process. But as Jeff's pulling up right now, you can see we can do etching into the material as well. So there's a couple ways to do that. You can probably very lightly etch on there is if you either reduce or turn off the abrasive flow and go over the material. You could see that there. Or you could just go quicker on the material at a faster speed. But one thing you will notice there is that at every one of those stops where the machine's trying to change directions, you will get a little deeper pierce there as well. Jeff, if you want to fill in too, I know you've got the most experience out of all of us of trying different feed speeds and depths like that.
Yeah, it works well if you need to etch a bend line where it's not super critical that these divots are here or not. So see that used quite a bit. It is a little bit of a messy process because the water and abrasive have nowhere to go. So you definitely want to have some sort of, we have supply a blue plunger cover to go over the cutting head to help keep that sort of spray down. But yeah, it's not the most refined process like you'd get on a laser, but it'll work in a pinch.
Excellent. So Ruth asks, she's looking to cut fruit. So cherries, apricots, peaches, plums. Do we have equipment that is good for food safe cutting? We've cut quite a bit of that over the years for test cuts and things like that.
We've got every now and then we'll get a inquiry on food. To be frank, the food industry is not something that we've gone after traditionally, just primarily due to health and safety regulations that generally come along with that. So while it's interesting to cut these materials when they come in, we've kind of deferred on those ones in the past. It's just not really our bailiwick.
Right. And Steve asks, what's the best way to handle small parts? Is it just through tabs or bridges, or is there a better way to support that material?
Depending on how much you need to do, you can do, as shown in this picture here in the corner, there's a water brick material, corrugated plastic, which is on edge, and then basically drilled together, bolted together. That makes a nice support for small pieces. You do have the consumable cost of that. That's going to get chewed up over time. So depending on how much you have of that to do, may or may not want to do water brick. Tabbing is certainly a good option. You can leave a small 10, 20 thousandths tab on the material and then just break it out. We've had some customers that do highly repetitive jobs of very small parts and have actually done things where we've come up with a fixture to support the pieces, kind of basically fins, very deep fins, 12, 18 inches deep in strategic locations to support those small pieces. and just space them very close together, which is kind of like in that video when I was cutting the glass. We had something like that where we had fins separated by about an inch in the X and Y to support that small piece of glass. We didn't need to tab that in there.
Excellent. And I think this one we could probably pull up that same slide that we had about the food is in researching fruit. I mean, what kind of water jet head or pressure have you used? I mean, I could answer that one, at least from the head perspective, is clearly that would be a pure water application. One, the material soft enough that you wouldn't need abrasive, and two, you wouldn't want to cut with abrasive because that could contaminate the food there as well. And it just got a few feeds and speeds up there as well.
Mm. Yeah, I don't remember specifics on this. I think the corn was pretty much full pressure because it's fairly dense with the husk. So to get all the way through the bottom, that was pretty close to full pressure. Something like fruit, you'd probably be able to do that. It's something like 20,000 psi. Of course, if you have still the stone in the middle, that can create a little bit of an issue there. So in lower left-hand corner, some dog treats is probably about like 40,000 psi on that. So generally smaller orifice, as you see on this one here, 6,000 orifice. So 4, 5, 6,000 orifice, basically the smallest orifice size that you can use to get through the material, and that's going to minimize your wetting and reduce your operating costs and increase the number of cutting heads that you can have on a machine. Generally, people are going to want to set up, as many cutting heads as you can and slide the material under that, convey the material under that.
Right. Now Steve asks, thanks Jeff. Steve asks, what kind of PPE do we suggest for people operating the WaterJet?
Certainly safety glasses, gloves, hearing protection, generally if you're going to be like around the machine all day. When the machine pierces and cuts, especially if you're slightly underwater, it's pretty quiet. If you get into doing something that's much thicker and it's taking you, something that's 10 inches thick and it's taking a couple minutes to pierce through, it can be quite loud during that initial piercing time. So generally probably want to have some hearing protection on. Some people, when they're putting abrasive into the abrasive hopper, they'll wear a mask. Of course, nowadays, pretty much everybody's wearing masks. But prior to COVID, sometimes a respirator, sometimes somebody might wear a respirator when they're putting the abrasive into the bulk feed hopper if they're having any coughing issues, because there's a little bit of dust with the abrasive. It's not hazardous. The garnet is inert substance, non-hazardous, but dust can sometimes irritate people. Steel-toed shoes, of course. So typical stuff.
Right. Excellent. And so we'll finish up. I know we're going a little over the time of the half hour, but Ruth did ask about selling the components of the system. So I can answer that as well. So for something like that, we have sold all different configurations, pieces, parts, and things like that. Really does depend on the application, though. So if you're looking for something specific like that, the best way to do is to contact us at sales@wardjet.com. and speak with one of our sales representatives, and they can match you up with the right pieces, parts, and system that would work for you depending on that application. So quite a bit does go into us matching up the right tools for the right job. So that's going to be your best way to start off with. And then one more question, even though I know we're a little bit over, is the garnet recyclable? So we have seen in the past, we used to sell a system that did recycle garnet. You can recycle the garnet. In fact, a lot of the manufacturers of the garnet are doing large scale recycling now, where you send in this spent abrasive, it's dried, it's then filtered out for some of the kerf material and things like that, and then reshipped out with recycled garnet. It does depend on what kind of garnet you're using as well, because there are certain garnets that when they're used the first time, they round, like the abrasive edges of those actually round off, of which that loses a lot of the cutting power. But there is, I believe, alluvial garnet will actually shatter, so it still retains the particles still retain that sharp edge, so it is able to be used again as well. In fact, in our recycling systems, we saw no discernible reduction in cutting power in the recycled garnet than we did over the fresh garnet as well. So Jeff pulled up a resource there. So GMA is typically who we use for our garnet, and related things there. So those would be, the GMA would be the best place to start with that, and we can always get you in contact there if that's something you're looking to do with a system as well. So with that, we'll wrap up. We want to thank everybody for taking time out of your day to join us on the webinar. Again, if you have any questions that pop up after this, feel free to reach out to us, sales@wardjet.com. We'll be happy to help you out, or if you're looking for a new system, match you up with the right tool for the right job. So thank you very much, Jeff, and thank you, everybody. We hope to see you next time.
Thanks, Benji. Bye.